So this is a session that should highlight the Higgs bundle program. And so I would like to make some short introduction and highlight more recent work with the applications to G2 and spin 7 holonomy spaces. Oops. As far as motivation goes, I think I don't have to explain that to this community, but the main, from physics, the main motivation is to study M theory, string theory compactifications on G2 and special holonomy spaces in order to obtain effective theory of consistent quantum gravity in 4 and 3 space-time dimensions with minimal supersymmetry. One focus in the study is to identify gauge degrees of freedom in these compactifications, as we have to obtain vector bosons of the standard model of particle physics. And these gauge degrees of freedom are expected to be encoded within the special holonomy spaces at certain codimension, namely codimension 4 AD type singularities. The gauge dynamics, the appearance of gauge group, gauge bosons in this context is governed by solving and dealing with specific Hitchin system on this codimension 4 spaces. So one specific goal is to actually identify not only gauge degrees of freedom, but also localized matter modes that would specify chiral matter like quarks and leptons of the standard model. And so as part of this program, I would like to highlight toward the end how localization of such modes was achieved in the G2 context of these constructions by adding the so-called Hitchin flux, namely by looking at the background of this Hitchin system that carries a lot of similarities with the so-called T-brane configurations. And this would be the highlight of the work that was accomplished last year. So let me start with a prototype system, namely Hitchin system in the Calabi-Yau threefold background. So the codimension 4 AD type singularity in Calabi-Yau fourfold is parameterized by the compact Riemann surface, and it's this Riemann surface that I wanted to argue that signifies the gauge degrees of freedom of corresponding D-branes that wrap this Riemann surface. So the gauge theory that appears on the Riemann surface is two-dimensional supersymmetric gauge theory, and as I argued, it is governed by a Hitchin system that is specified first by a connection of a vector bundle, but also now by the one form Higgs field, both of them living in the being joint valued in the corresponding non-abelian ADE type groups. So these degrees of freedom go under the name of the Higgs bundle, and the corresponding equations of motion, Hitchin equations of motions that the Higgs field and the vector bundle connection satisfy are have deep connections to the first order so-called BPS equations. We expect that the actual properties of these solutions, in particular the Higgs field itself, characterizes for us the formations of the shape near the singularity in the ambient Calabi-Yau space. And similarly, the gauge connection parameterizes corresponding gauge degree of freedom deformations, the so-called flux associated and sourced by these D-branes. Within G2 context, we are dealing with one dimension higher codimension for singularity. So namely to describe gauge degrees of freedom in G2 background, they are realized now on three-dimensional manifold, again associated with codimension for AD singularities. And this was studied by Pantev and Weinhold, but also in an earlier work of Bobby Acharya and follow-ups by Rodrigo Barbosa. So the gauge degrees of freedom on this three-dimensional submanifold are governed by three-dimensional field theory that could be described as particular topological three-dimensional field theory associated with now D-branes wrapping this manifold. And again, the degrees of freedom there are now specified by a Higgs bundle, namely there is a vector bundle connection, but also now the one-form Higgs field valued now also in this three-dimensional space. And there are corresponding first-order differential equations that govern these backgrounds. Now, when searching for chiral matter in this context, it was proposed to look, in this case, at a configuration of the background field, and the chiral modes are expected to vanish where this background field vanishes. And that was further elaborated and further studied in extensive study by the Oxford group that also extended this analysis to include now also codimension 6 singularities that signify not chiral but non-chiral matter. And another very appealing feature of this approach was that it could possibly also connect to building compact G2 manifolds. So it ties actually this construction to compact G2 manifolds that were obtained via twisted connected sums. Now, as far as backgrounds of the Higgs field and the gauge connection, namely flux, goes, up to last year, not much was really done beyond looking at really diagonal form of the background field, namely the parts when this Higgs field components commute. And actually the gauge flux was not turned on either. So the work at the at Penn actually generalized the study. Namely, what we addressed is looking at this Hitchin type system that generalizes the background to include also non-diagonal one form Higgs field, as well as this non-zero flux A. So typical structure of this background is includes off-diagonal terms, and as a consequence, the components don't commute anymore. And this type of background is very reminiscent of the T-brane configurations addressed for the Calabi-Yau fourfold, in the Calabi-Yau fourfold context. So that's why we also refer to them as T-brane configurations. As a specific solution to Hitchin type equations for that type of Ansatz of the background, we really address that only within a local model. So this three-manifold was locally described as a Riemann surface over fibered over an interval. And so the corresponding gauge theory that we are deducing in this context with that type of fibration turns out to be on this Riemann surface really a very mild deformation of the original Hitchin system I was referring to earlier. And this type of local construction actually, like the Riemann surface, Hitchin system of a Riemann surface describes local Calabi-Yau geometry. This ansatz for the three-dimensional space and the corresponding gauge dynamics there naturally fits into studying local deformation of TCS type constructions. And so it can be naturally interpreted at least as a building of a local G2 background within this context. And another important result that actually motivated us primarily is to address localized codimension 7 modes. And it turns out that for this T-type, T-brain type configurations, we could find, at least in this local context, explicit localized mode solutions. So this background indeed provided for us, at least locally, the existence of localized matter solutions. And we also argued that this, in more general context, the existence of these solutions can be studied in a more abstract way, and it reduces to a certain algebraic problem that is very reminiscent of T-brain configuration in Calabi-Yau fourfolds, as I mentioned. Well, this is the old story, a year-old story, and it's natural to extend some of the studies within G2 backgrounds to take this three-dimensional gauge theories and fiber them over another interval. So we would be dealing now with the gauge theories in 4 dimensions, which are expected really to describe locally now spin 7 backgrounds characterized by the specific construction of gauge theory on a 4-dimensional subspace. So that work was actually advanced quite recently, as well as work in progress. And that really naturally leads me to the main topic of Gianluca's talk. Thank you.
Thank you.
So maybe, yes.
Can I ask at this point if there are questions?
Okay.
Any questions? Speak up. If not, we go on with.
So you mentioned that your 3 manifold is modeled on a kind of a Riemann surface fibered over some circle.
Right, an interval, yes.
A special ansatz, or is that meant to?
This is a special ansatz. For example, in the original work, Pante-Weinhold took S3 as a prototype. It's really a specific ansatz for the 3-dimensional manifold. In order, we were motivated also to tie it to TCS constructions, because you sort of expect that to be part, the singularity, codimension for singularity, at least locally described, the way TCS constructions were approached. And I think we'll hear more about also in this context. We are dealing with as vibrations over interval and another vibration over interval as possibility to go all the way down to specific way of describing spin 7 gauge dynamics.
So I would imagine that if you don't take this kind of special form, you would probably get some more equations more like monopole equations rather than Hitchin systems. Is that roughly correct? Or?
Well, yes, likely, yes. I think at least the abelian cases, some of that was studied in Pante and Weinhold examples. Yeah. I think it's, here we really were tying it to the Hitchin system, right? Because we had this fibration of a Riemann surface over the interval, indeed. Okay.
And to your knowledge,
Okay.
monopole story hasn't been worked out? Or?
Maybe Rodrigo, can you maybe say something on that? Or yeah.
What is it?
If you take the three manifold to be just three sphere S3, those are the prototype examples that Panta van Weinhold took originally, right? And the equations for this, for the Higgs bundle degrees of freedom don't naturally split into Hitchin type, right? They are more of a monopole type.
Over S3, you don't have non-trivial solutions because, you know, this, you can describe this in terms of complex flat connection.
Mm-hmm.
So you have to excise a link.
So you're going back to flat case, right?
Well, the solutions could be singular, right? So you could either excise these loci, or you could have singular Higgs field configurations. So that's basically what we studied, and also what Max studied in his paper today.
We also happen in our ultra local case, we also saw singularities out of this region as well, right? That's
sure.
But yeah, the full global understanding, of
maybe
compact three-dimensional space there. It's really not what, it hasn't been addressed really,
Well, I think, yes, you just have to, you will have only trivial solutions if it's not singular. And if it is singular, then there are solutions, and you can get chiral matter, codimension 6, 7 singularities. It's just the G2 itself is, of course, non-compact because the ALE fiber is non-compact.
Right. Well, just to maybe repeat again what we've done, we basically done it with fluxes. This is, it's sort of like another direction that one sort of realizes possibility for localizing zero modes as well. Okay, so maybe I should give at this point a chance to Gianluca to continue with the really more recent work that is now extending related analysis to C7.
Okay.
Oh, great. Okay.
Yes, I will start by sharing my screen.
Okay.
Let me see. Go to full screen. Okay. So as Miriam mentioned, I will continue and talk about this paper that we published this year in March with the people at Penn. And we discussed how the spin 7 system, the Higgs bundle that appears in spin 7 compactification can actually lead to some kind of unification of other Higgs bundle systems. So I will go quickly over other systems that that will appear in the following. The first one is the BHV system that was introduced in 2008. This is a Higgs bundle on a Kähler surface, so it's a complex two-dimensional manifold. In this case, you have a Higgs field that is a complex form of 2,0 type that takes value in the adjoint representation. And you can write supersymmetry equations. They are basically the kind of differential equations that govern this system. And this basically fixes the Higgs field to be a holomorphic section of this bundle. The bundle itself has to be all holomorphic. And moreover, there is a notion of stability that fixes part of the flux in terms of the commutator of phi with this dagger. Just to point out that the dagger is taken basically as a Hermitian conjugate because we work in a unitary frame, and the Kähler form is this quantity that I call J. So in physics settings, this appears when you take F-theory compactifications on a Calabi-Yau fourfold manifolds. And since you have to deal with the holomorphic structure, this actually it's rather easy to build solution. You have a lot of tools to do that. The next system is the one that appears in G2 compactification that Miriam already described. So this was introduced by Panta van Weinhold, and there's been some interest recently, including a paper that appeared today by Max. In this case, you consider a 3-manifold, and the Higgs field is a 1-form. The supersymmetry equations basically fix phi to be closed and harmonic and co-closed. So it's basically harmonic, and the flux is related to the commutator of phi with itself. When I write this commutator, actually, I implicitly assume that there's a wedge product between hidden in it. You can also rewrite this using a complexified connection. So basically, you fix the curvature of this complexified connection to be 0, and you keep this condition of fixing phi to be co-closed. So if you you may notice that this is very similar to kind of Hitchin system, though it's like an extension on a 3-manifold. It's a way of writing the Hitchin equations with a different complex structure on the Hitchin moduli space. And as Miriam already stressed, this appeared in M-theory compactification on a G2 manifold, where the G2 manifold is basically an ADE fibration over Q with the structure determined by phi, the Higgs field. So now I will go to the next one, which is the main actor of this talk, which is the spin 7 system that was introduced in 2018. So in this case, you have a Higgs bundle on a 4-manifold. This can be any kind of 4-manifold. You don't need it to be complex. The Higgs field is an adjoint valued self-dual 2 forms. And the equation that govern this system basically fix phi to be closed and therefore also a harmonic since it's self-dual. And there is part of the flux, there is the self-dual part that is fixed in terms of this cross product of phi with itself. So as I mentioned, the subscript SD means that we are talking about only the self-dual part of the curvature of the bundle. And this cross product, which maps two self-dual 2 forms to a third self-dual 2 form, is defined in the following way using the metric. So you may notice that this system is very similar to a Vafa-Witten system, though in that case you have an additional scalar. This appears in compactification in M-theory on a spin 7 manifold, and locally the spin 7 manifold is reconstructed as an ADE fibration over the 4-manifold M, and the structure of this fibration again is determined by phi. And what we want to stress in the following is that the previous system we talked about actually are particular solution of the spin 7 system. I will highlight this starting with the penta-Weinhold. In this case, you can specialize the 4-manifold to be the product of a 3-manifold times a circle. For this kind of manifold, you can actually write self-dual 2 forms as using a 1 form on the 3-manifold, which we call phi hat. And here dt is basically the distinguished 1 form on the circle. When I write the star, I mean the star on the 3-manifold Q. So you can use this form of the self-dual 2 forms and basically rewrite the spin 7 supersymmetry equations. If you basically, there are some terms that if you set to 0, you recover the penta-Weinhold system. The terms are the ones that I underscored. And to really recover the penta-Weinhold system, including also the correct number of degrees of freedom, basically you need to set the holonomial along the circle to be 0 and have no dependence on the circle direction of all fields. So basically you can think of the penta-Weinhold system as the dimension reduction of spin 7 along the circle direction. We can play the same game for the BHV system. In this case, you need to specialize the 4-manifold to be a Kähler manifold S. So in this case, you can take the bundle of self-dual 2 forms. This admits a Hodge decomposition. It has 3 components, 2, 0, and the conjugate 0, 2 forms, and there's non-primitive 1, 1 forms. And you can, again, write the spin 7 equations in this setup, specialize into the different kinds of Hodge types. And basically, you find that you recover this BHV system whenever this 1,1 component of the Higgs field is set to 0. So basically what we've shown is that there is a BHV system containing a particular solution on spin 7 and penta-Weinhold as well. The question is, can you connect a BHV to a penta-Weinhold? That is, can you build for some particular form manifolds a bridge between a BHV solution and a penta-Weinhold solution going through a spin 7 solution? And the answer is yes. So the kind of manifold we consider are basically the product of a Riemann surface and a cylinder. We do this because we want it to be Kähler and also to be the product of a circle times a 3 manifold. So, so basically this is a cartoon of this kind of manifold. I call Z the coordinate on the Riemann surface, which whose real components are X and Y, and W the complex coordinate on the cylinder, whose real components we call T and theta. Theta is the circular direction. So to make sure that we go from a penta-Weinhold to a BHV solutions, what we need to make sure is to get the correct boundary conditions, basically. So what we want to ask for is that the 1,1 component goes exponentially fast to 0 as t goes to -infinity. In this case, you approach a BHV solution. Here, lambda, the various lambdas are some constants that are always taken to be positive. And for t plus infinity, on the other hand, we want to recover penta-Weinhold. Therefore, we ask that the holonomy along the circle goes to 0 and the theta dependence of all fields goes to 0. In the middle, between these boundary conditions, basically you have a generic spin 7 solution. And let me mention that this is basically the Higgs bundle version of the GCS construction of spin 7 manifold. This was introduced in 2018 by Andreas Braun and Sakura Shafe-Nameki. This is like similar to the twisted connected sum construction of G2 manifold, only here you end up building a compact spin 7 manifold using as building blocks a Calabi-Yau 4-fold and a G2 manifold, knowing the connection between G2 manifolds and penta-Weinhold system, and on the other hand, Calabi-Yau 4-folds and the BHV system, we see that basically this is a local version of this kind of construction. So we end up building a non-compact spin 7 manifolds at the end of the day by gluing these two components. To be more explicit, you can build some example. I will go quickly through it. You can take the Riemann surface to be a torus for simplicity, and we take abelian solutions. So we take phi cross phi be 0 and no flux. So the equations become linear. You can write them as a linear superposition of a BHV solution and penta-Weinhold solution. You just need to ask each component to fall off as desired by the boundary conditions. The BHV solution is basically the product of one forms on the Riemann surface and on the cylinder. We need some poles on the cylinder to make sure that you get the right boundary conditions. And the penta-Weinhold solution is a bit more complicated. We can build it using holomorphic forms. And the trick we use to build this solution to make sure that they actually are a solution of the equations is to form these complex coordinates, which works only in case the Riemann surface is a torus. You can play a similar game. So since I don't have much time, I will go quickly through it, but just mention that you can build penta-Weinhold to penta-Weinhold interpolations. In this case, the 4 manifold is a 3 manifold times a line. And physically, what we are interested in this because this produces some interfaces in 4-dimensional theories. we can build this taking the tree manifold to be a torus for simplicity, and build solutions that are similar to the ones I highlighted before. You basically select a 2 torus inside the 3 torus, build a penta-Weinhold solution on these 2 torus times the line. This is a prototype solution that has the right asymptotics. And then we can build others, maybe flipping the asymptotics as well, and then superimpose them. And well, I don't have much time, so I will go quickly through the 0 modes part. We also discussed 0 modes, which are like the infinitesimal variations around the solution, around a given background. We have a system of equations that control them, and they are always defined up to a gauge, up to an equivalence via gauge transformations that I wrote here. This is a kind of cohomological problems. They can be put in terms of a complex. The differentials, I didn't copy them because they didn't fit into the slide, but basically are given by the ones that produce the correct equations of motions and the gauge transformation. So what we are actually looking at is knowing the this cohomological problem is basically looking for the kernel of this delta 1 operator, mod the image of the delta naught, which is the equivalence given by gauge transformations. And interestingly, we can wonder where are they localized, if there's some localization property. For a Abelian solution, we can do this. One way to analyze this is to use spectral covers. For instance, for a unitary group, you can take the usual determinant of phi minus the identity, basically, and see where the sheets of the spectral spectral cover intersect. Actually, here spectral covers are basically defined by 3 components because locally the bundles of dual 2 forms has 3 components, and the kind of localization we expect is in codimension 2 or in codimension 3. Adding other ingredients will change the story, but this is this, at least with these ingredients, this is the kind of localization we expect. And let me go to my conclusions. So we studied Higgs bundles that appear in spin 7 compactification of M theory, and these are very interesting because they can provide a unification on other non-Higgs bundles. You can build interpolation between solutions, connect them, and also interfaces that can have a physical interest between some penta-Weinhold solutions. And this is more or less what I wanted to say, and thank you for your attention.
Thank you. So we can open up to questions.
Oh, sorry, may I ask a question?
Yes, go ahead.
So you introduced something called spin 7 system, and you wrote some equation and some complex. Is it elliptic?
I believe it is, but we didn't discuss this. So there's a similar story for the
Okay.
Waffa-Witten system, but yeah.
But you don't have scalar field or something.
No, so the Waffa-Witten system
bundle is different from the Waffa-Witten case.
Exactly, yes. There's no scalar field.
In one of your last slides, you had a complex. It looked as if it's been chopped off at the end. Is that an elliptic? I mean, it looks as if there might be a term out. You've got 0 at the end. Is that an elliptic complex?
Perhaps you might be missing some.
It looks as if there's something missing at the end. But yeah.
Yes, the simple calculations shows that it doesn't look like elliptic complex.
Yeah, yeah. It looks as if you're adding 2 things together.
Yes, exactly.
Okay.
That's a small point, sorry.
Yeah. Okay.
Thank you.
Any other questions? Other questions?
I had a question. It's okay.
Yeah.
Have you? This gives a local description of, I guess, local spin 7s. Is that right? Which have these ALE fibrations.
Yes, that's correct. Yes.
Have you? I mean, I guess some known local spin 7s have ALE fibrations. Have you had a look at what your equations look like in those cases?
So we didn't look at known examples. We were more interested in the trying to characterize the system and build this kind of interpolations between solutions.
Right.
But so the system of the equations will fundamentally be the same. What changes is just the profile of the fields, which should probably be purely geometric in that case. So there is no flux and only an abelian phi turned on.
Mm-hmm.
I have a question.
Yes.
For the spin 7 system, did you look at any concrete example and do the zero mode counting?
The zero mode counting is well, it's a kind of an open problem. We just discussed without giving example. Let's say we only discussed the abelian case. We are trying to do more building, trying to analyze the zero mode structure for non-abelian solutions, which is generally more complicated. But yeah, so we only discussed the cases that I highlighted in the slides. So
yes,
we didn't have, sorry.
No, go ahead.
We didn't have a counting prescription, basically. So the tool we used is the spectral cover. And looking at the structure of the spectral cover, you can discern where there are localized modes.
And did you have any local spin 7 or other systems over a compact manifold, or you always use the flat metric as well, I think, right?
That's correct. Yes, we only looked at solutions on non-compact for manifolds for simplicity. The gluing prescription that we used, the gluing kind of gluing that we discussed, was mainly inspired by the twisted connected sum construction, because there's also a cylindrical region in that case, but we didn't try to compactify the solutions.
Okay, I see. Thank you.
Sure.
So can I ask, in these examples, these very explicit things where you wrote down the Higgs field and so on, I mean, can you then write down spin 7 metrics explicitly from that? Or?
So what you can reconstruct using the Higgs field is the the hyperkähler structure from the on the ADE fibers, because basically the phi corresponds to a deformation of that. It should be sufficient to reconstruct the metric, I guess. But maybe someone knows more about this than I do.
Okay, thanks. So maybe we can thank Gianluca again. And I guess there's still time for discussion on Higgs field.